Section 2.3 Measures of Central Tendency. Last week, we talked about some measures of central tendency, notably the mean, median, and mode. I want to go over these in more detail today. First, let's talk about the mean. Another way of talking about the mean is talking about the average. It's the same thing. I've got several numbers here on top: 12, 18, 24, 30, 33, 39, 52, 60. There are 8 numbers there. So if I add 12 plus 18 plus 24 all the way to 60 and divide that sum by 8, I get 33.5. Now the mean for a sample is simply what that mean is for that small group, that small subset from the population. For example, we have 28 students in our class. I select 7 as a sample, and I find out what's the average age. That the sample mean would be the average age of all of those 7 students. Population mean would mean I take all 28 students and find out what the average age is. Now, as I talked about last week, we also have a set of data here, 30 individuals, and how old they were the first time they got prescribed glasses. Lowest being 12, highest being 65, and I've sorted from lowest to highest. If I add all these numbers up, the 12 to 14 plus 14 plus 14, all the way to 65, I get 952. 952 divided by 30, because there's 30 samples here, is 31.73. So the mean or the average of the ages for this group of 30 individuals is 31.73. And I put it on this graph here to see roughly where it falls. The median is the middle number. When we have to order our set from lowest to highest, which you have to do, it is that number that sits in the very middle. Now, what you see what I got here is 12, 18, 29, 42, 61. There's 5 numbers here. There's 2 on this side, and there's 2 on this side. So I find the middle number, which is 29. The median for this set of five numbers is 29. It has nothing to do with the average. It is the middle number. It's like the middle of the road. This is called the median. Now, this is if there's odd. Below this, I've got 6 numbers: 2, 3, 4, 7, 8, 12. And what I have here is I can't find a middle number. I have 3 on this side, just 2, 3, and 4. And on this side, I have 7, 8, and 12. So what I actually have to do is I have to find, and I've always circled it right here, I have to find what is the halfway mark between 4 and 7. 4 plus 7 is 11, as I've got in the bottom here. And there's 2 numbers, so divide by 2, 11.2 is 5.5. And that makes sense. The median, or the middle number for this, is 5.5. It doesn't actually have to be a number on there. 4 plus 1.5 is 5.5. Another 1.5 is 7. So yeah, 5.5 makes sense. And it would basically be right here. I'm going to write it down here. Now, with our group of 30 individuals and how old they were the first time they got glasses, there's 30 numbers. It's even. And I've already sorted this. You need to sort it to find your median. And the 15th number is 31. Got an arrow there. And the 16th number is 31. Well, what is halfway between 31 and 31? It's 31. Technically, I could add 31 plus 31, which is 62, divide by 2, because those numbers, again, equals 31. The median is 31, not exactly 31.73 as in the previous graph, but pretty close, but not exactly the same. Now, the mode is the most common. It's easiest to remember mode by mode and most. I've got some numbers here: 12, 14, 14, 14, 14, 19, 19, 21, 21, 21, 24, 25. The mode's 14. There are 3 14s. 4 14s. You see right here. 1, 2, 3, 4. Now I've got another set of numbers here from 15 up to 41. And I've got two sets of numbers that are modes. 17, there's three 17s, and there's three 19s. There's two 29s, but that is not as much as three. So three 17s, three 19s, that's called bimodal. You can have more than one mode. Now, if we look at this data set again of how old someone is first time they got glasses, there are three 14s, there's two 20s, there's three 27s, two 31s, two 32s. But then I get there's five 40s. So that's the mode. That the most of any individual number is 40. There's five of them. And if I graph this here, you can see the mode is a little higher up than the mean or median. In fact, if I go to all three graphs and put all the mean, median, mode together, they're not the same. They're in the same area, but they're not the same. This is a graph of data with the number of individuals on the y-axis and how many books they read on the x-axis over a year. And you can see the mode is the most. The mode is the most by volume. It looks like we had about maybe 60 students that read six or more books each. So the most common class is six, because that's the highest mode. This right here. This is the highest one right here. The median is the middle number. If we find that if we had all these individual numbers, the median would be next to the mode. Probably half on one side, half on the other in terms of individuals. Then the mean is even farther down. Because while there are more, you got from one to about seven number of books some people read. There's only 1, 2, 3, 4, 5, 6, 7 of those categories. Now on eight or more books, there's 8 of those categories. Now there's less by number of people reading 8 or more, but there's more categories. So that's why the mean would fall right within that. It's halfway on one side, halfway, or the average halfway on one side, halfway on the other. As the mean, the middle, not the middle, the average books read. Again, it's not the same as the median. Now, if you have the mean equal the median equaling the mode, that is called a normal distribution. We're going to talk a lot more about that the rest of the semester. But we need to recognize some things first. The mode, it's the largest one because it's the highest here. The mode, most common one, is 8. The median is the middle number. This is symmetrical. We'll talk about that in a minute. So there's half on one side, half on the other, because it is symmetrical. And then the mean, the average, would fall right in the middle there too if we looked at these numbers. Now, before we go any farther, I want to talk about weighted means. One of those common examples we use here in college is grades. If I have a student who took 4 courses, and remember, an A is 4 points, B is 3 points, C is 2 points, D is 1 point, F is 0 points. And they got a B in history, which is worth 3 points. Biology lab, they got an A, which is worth 4 points. Sociology is 2 points. Physical education, they got 4 points. So they got 2 A's, a B, and a C. If I look at that, I could add 3 plus 4 is 7, plus 2 is 9, plus 4 is 13. So by grades, 13 divided by 4 classes is 3.25. The problem is we're making an assumption here that all the classes are of equal value, and they're not. History and sociology are worth 3 credit hours, and the biology lab and the physical education are worth 1 credit hour. So we're given the same weight by doing it this way to the 1 credit hour classes as the 3 credit hour classes. The reality is we have to weight by credit hours, in this case, those classes. So we have not considered that history and sociology have 3 times as long of class as a biology lab or the physical education. We're spending three hours in history and only 1 hour in the biology lab, and we're making them equal. We don't want that. You should have consideration for it takes 3 times as long to do history and sociology compared to biology lab or physical education. We are really overpowering and overrepresenting the small classes, 1 credit hour, and underrepresenting the history classes and sociology classes. So we weight it. And I still got those same grades. A B is 3, an A is 4, a C is 2, an A is 4 for this history, biology, sociology, and physical education. But the credit hours for each one, history is 3. So I take the grade, multiply it times number of hours. 3 times 3 is 9. Biology is only 1 hour, so it's 4 times 1 is 4. Sociology, I got a C in there, 2, and that's for 3 credit hours, so that'd be 6. 2 times 3 is 6. And then physical education, 4 times 1 is 4. Now I add up those score times credit hours. That's the weight. That's my weighted scores. 9 plus 4 is 13, 6 is 9, 4 is 23. So when I add all those up, 9 plus 4 plus 6 plus 4. And then and that's 23, and divide by number of hours I took, which is 3 plus 1 is 4, plus 3 is 7, plus 1 is 8. 8 hours. 23 divided by 8 equals 2.875. That's quite a bit lower than the 3.125 we had. Now, a real life example, I could look at some surveys I did. I talked to one group of 200 people, 80% like Coke, 20% like Pepsi. I talked to another group of people, this time 1,000, 50% like Coke, 50% like Pepsi. And what a lot of people do, and this is wrong, is they'll say, okay, I'll take 80% for the one that likes Coke, 50% of the other likes Coke, 80 plus 50 is 130% divided by 2. That's 65%. That's assuming the groups are equal. They're not. One group only has 200, the other group has 1,000. And we have to consider that. Again, the weight of the first group with only 200 is overrepresented. We're saying they're equal to group 2. And by doing it the way I was just showing you, that means group 2 is underrepresented. So we have to weight it. I'll take the first group, 80% like Coke, multiply times 200 people. 80% times 200, 160 individuals. Group 2, 50% people like Coke. Out of 1,000 individuals, that's 500. So if I add 160 plus 500, that's 660 people among the two groups out of how much total? 201,000 the other, that's 1,200. So 660 divided by 1,200 is 55%. Much lower with a weighted average than the 65%. And this is why we need to weight, because we get a more honest answer based on the volume within the different groups. Now, as I talked about, we had normal distribution, also known as a bell curve. What makes a normal distribution is where the mean equals the median equals the mode, and they're symmetrical. I could cut it down the middle and flip it on one side or the other. But a normal distribution has mean equals median equals mode. A uniform distribution is they're all pretty much the same. This is exactly 4, but between 4 and 4.5. You can see there's not, a mode with a median and a mean all in the same spot. It's just rather consistent all the way across. Now, talk about skewness. In the middle, it's a very low curve, but this is a normal distribution. Very low bell curve. But it's symmetrical, half on the left, half on the right. Mean, median, mode is in the same spot, above that 0. Now, left skew or a negative skew, you see it's not symmetrical. They call it left skew because the tail is on the left, as I've circled here. Right skew, or a positive skew, has the tail on the right. Now, what makes this different, why it's not a standard distribution, I'll show you in the next slide. A negative skew or left skew, You can see the mode is the highest, but then there's the median, a little lower, and the mean is the lowest. It's flipped on the right skew, the positive skew. Mode is the highest, but then to the right of that's the median, but then to the right of that is the mean. And if it's a symmetrical distribution, it's a normal distribution where the mean equals the mode. You can see on the left and right skew, the means, medians, and modes are distributed differently than with a symmetrical distribution. Now, kurtosis will have a normal distribution, but what we're looking at here is the range. If I assumed each one of these is a group of 1,000 individuals, there's a greater spread or range on the negative kurtosis, which is also called platykurtic. A platykurtic curve is kind of pushed down. There's 1,000 individuals under there, but it's a very wide range. It goes, look, whatever our scale is here, it goes like -10 to +10. A normal distribution where it goes from -5 to 5, that's the same 1,000 under that curve, but you see the range isn't as big, and that's called a mesokurtic curve. Meso meaning middle. And then a positive kurtosis, a leptokurtic curve, is very tight. You can see that range is very small. In fact, it looks like it's about between -2.5 and 2.5. So the kurtosis will have normal distribution, but what we're looking at here is the range or the spread of the data. Is it real wide, such as a negative kurtosis, which is again platykurtic curve? Is it normal, as with the mesokurtic curve, a normal distribution, or is it positive, leptokurtic, where it's a very tight distribution, where it's distributed very closely to that center line? Now, obviously, with the platykurtic, the peak is at its lowest, the leptokurtic has the highest peak, and the mesokurtic is a normal distribution. We see these when we're looking at, for example, heights of individuals. For example, I've often said that the average height, if I took a 1,000 people in the United States, might be 5'6". I'd have a normal distribution. But if I did the average height of the NBA players, it could be leptokurtic, very tall. And maybe, 90% of your players are probably over 6'3".